So here we'll talk a little bit more in depth about sequences. So let's suppose f is a function such that f of n is equal to a sub n for all positive integers n. If the limit as x goes to infinity of f of x is equal to L, then the limit of the sequence a sub n is also equal to L. So basically this says if we have an explicit formula for our function, I can take the limit as that function goes to infinity, and then that is going to be the limit of the sequence. So let's assume that our sequences a sub n and b sub n have limits a and b. Then if I add up the sequences, I can just add up their limits, the same thing with subtracting. Multiplying a sequence by a constant will give me that constant times the limit. Multiplying two functions gives me the product of their limits. And dividing will divide the limits. So these are some basic properties of limits. So let's determine the limits of this sequence. So the idea is I'm going to look at the limit as n goes to infinity. 2 over n squared plus 4. And if you remember from Calculus 1, if the degree on the top is the same as the degree on the bottom, we just need to look at the coefficients. 2 over 1, which is 2. So this sequence will converge to 2. Let's look at this one. So the limit as n goes to infinity of 4 over n cubed of 7n plus 2. We can see that the top is growing a lot faster than the bottom. So this one will actually be infinity. This sequence will diverge. There are some terminology for sequences. So if we have a sequence a sub n in which a sub n plus 1 is greater than or equal to a sub n, this is said to be non-decreasing. So this would be a series like 1, 2, 3, 4, 4, 4, 5, etc. So basically, we can have our terms either getting bigger or staying constant. We say it's non-increasing when we have the opposite of this. Our terms are getting smaller or staying constant. We have 12, 11, 10, 10, 7, 3. So this is non-increasing sequence since our terms are either getting smaller or staying constant. A sequence that's either non-increasing nor non-decreasing is said to be monotonic. So this means it only progresses in one direction. And finally, if there's a real number m, such that the absolute value of all of the terms in the sequence are smaller than this value, we say the sequence is bounded. So next we're going to look at a particular type of sequence, a geometric sequence. This is where each term is obtained by multiplying the previous term by a fixed constant. And they generally have the form a times r to the n, where this r is called the ratio. So let's consider these values. So let's start with graphing minus 0.5 to the n. We'll let this be 1, 1/2, 1/4, etc. So 0.5 to the first power is 1/2. Squared is 1/4. Cubed is 1 over 8. And then to the fourth power would be 1 over 16. For the second one, negative 0.5 to the n. I'm going to say this is 1/2 and 1/4. Down here I have negative 1/4 and negative 1/2. So negative 0.5 to the first power is negative 1/2. Squared is positive 1/4. Cubed is negative 1/8. And then to the fourth is positive 1/32. So we can see that the first one is moving down towards 0. So this one is non-increasing. The second one is alternating positive and negative, so this is not a monotonic function. However, you can see that both sides are moving towards the axis. So it looks like both of these are going to go towards 0. Next, let's look at 1.5 and negative 1.5 to the n. So looking at the first one, (1.5) to the first power is just 1.5. Sorry, right about here. 1.5 squared is going to be 2.25. Cubed will be 3.375. And then to the fourth power, 5.0625. So we can see that these are getting bigger and bigger and bigger. The only difference whenever I do negative 1.5 is I'm going to be alternating. I'll have a negative, and then a positive, and then a negative, and then a positive. However, you can see that both sides are going out. So it looks like these are going to both diverge. And in general, that's the case. If I have a geometric sequence and my ratio has an absolute value that's smaller than 1, my limit is 0. And these were the two first cases. 0.5 and negative 0.5 have an absolute value less than 1. The absolute value is greater than 1, which was those second two cases. The limit does not exist. And if it's equal to 1, then I just have the sequence 1, 1, 1, 1, 1. So the limit is just 1. So the last thing we'll look at is the squeeze theorem. So here I have two sequences where a sub n is less than b sub n is less than c sub n for all integers n greater than some number n. So if the limit of a sub n is equal to the limit of c sub n, which is equal to L, then the limit of b sub n is equal to L. So kind of the idea of what's going on here is I'm going to have some function a sub n. And then I have some function c that looks more like this. And then we know that b is in the middle. And if I know that this point right here is all the same, if I know this is the limit of a sub n and of c sub n, then it has to be sub b sub n. So this is kind of squeezing our middle function into a certain point. So for example, let's find this limit. So we know that sine is always between 1 and negative 1. This also works for cosine. So this whole function is between negative 1 over n cubed minus 2. And then on the upper side, 1 over n cubed minus 2. And as I take the limit as n goes to infinity of these, I will get the limit of negative 1 over n cubed plus 2, or minus 2 is 0. And then the limit on the right is also 0. So the limit as n goes to infinity of a sub n will have to be 0.